start recording with what's going on. So where we ended last week was looking at oxygen nucleophiles. Right? So our oxygen can attack our carbonyls because our carbonyl carbon is electrophilic. And what we had looked at was water as our nucleophile, or our source of oxygen. We could switch that up to now being an alcohol. So if we convert to an alcohol, we have an interesting effect coming out of this. We can do that reaction twice. Okay? So our nucleophilic oxygen from one alcohol attacks our electrophilic carbon, and it can do it a second time. The net result is we push all the way to what's referred to as our acetal. And we've done a complete swap out. We have two OR groups, and we've kicked out water. Okay? The oxygen from our water was the carbonyl oxygen. They are one and the same. Okay? Anybody notice any kind of quick ideas from this? What happened to the reactivity of our carbonyl at the end of this reaction? Do we have a carbonyl anymore? No. So here's a protecting group. We can react a carbonyl with alcohols and convert it into an acetal. The acetal is no longer a carbonyl, which means it won't react with our lithium aluminum hydride. There's a protecting group. Okay? We do run into some issues with this reaction, though. Okay? The biggest one is going to be equilibrium. Just like we talked about with our hydrates and water, we're in an equilibrium situation. So our reaction can go both forwards and backwards. And in most cases, it does not prefer the acetal. Okay? Yes, Simone.
Sorry, can you go back to the last slide one more? Okay, thank you. I just need to get, I was wondering if it was just water.
Okay, yeah. And I think that next one, oh, no, it is there. So on this one, what happened is I broke it up into the smaller steps. So we end up going through and forming an intermediate species called the Hemiacetal, which really just means halfway to being an acetal. Right? So that's after a single addition to the carbonyl. So in these reactions, what is our nucleophile? What is a nucleophile in general? Negatively charged species. Nothing's negative. We need a lone pair of electrons to share. Okay? What is our electrophile? Okay, our electrophile, definition of our electrophile is a positively charged species. Is there a positively charged species? There's a partial positive charge, which is our carbonyl carbon. Okay, so what we're trying to do is identify our positives and our negatives and attempt to hook them up with each other. Okay? If we look at our overall reaction, which way would we expect this equilibrium to go? Reactants or products? That was a fun response. I got two people holding up thumbs, and they pointed the opposite directions. Okay, it's a bit of a challenge. In general, it typically favors the carbonyl. Okay? Very rarely do we actually push towards the acetal. We can do it, but we have to push particular circumstances to get that to occur appropriately to any high amount. Okay? One thing that we could look at to help favor our carbonyl, talked about entropy. Which side of the reaction is favored according to entropy?
Oh, entropy.
Entropy. What we're looking at is how many reactants do we have? 3 versus how many products? 2. Entropy favors the side with more species, which is a reactant side. More disorder. Entropy is always going towards more disorder. So if we look at this reaction, it's not a particularly favored reaction to occur. Okay? We can take it a step further and look at, since it is equilibrium, trying to speed it up to equilibrium. Because will it make some small amount of the acetal? So maybe we can speed up our reaction a little bit to start to make some of the acetal. Once it's made in the lab, what could we start to do? We could start to pull it out. Why would pulling it out help us out?
Because then it'll backfill.
It'll backfill according to Le Chatelier's principle. Okay, so we can start to favor the formation of that acetal product by removing one of the products, which can now start to push and continue to give us more and more of our product, and we can get that conversion to occur, even though the equilibrium is disfavored. Okay, so that's kind of nice. But if we have to wait 2 years for it to get to equilibrium, that's going to be a bit tedious. So how could we speed this up? Catalysts. Okay, what catalyst could we add? What's that? H2 and Lindlar's is just going to reduce our carbonyl at best. Okay, we don't want to reduce the carbonyl. We want that carbonyl to react selectively with our alcohols. Okay, when we're looking at speeding up reactions, there's really only 2 things that we should be looking at. And as a pseudo hint, there's one, there's the other. And here, let's even get fancy with color coding. What's in our red box? Bad movies. Our red box has the carbonyl, but just because it's a carbonyl, that's pretty useless. We want that carbonyl to do something. What does it need to do? It needs to act as an electrophile. So if I want to make this reaction go faster, what should I do to the electrophile? Make it more positive. What can I do to that structure to make that carbon more positive?
Put a hydrogen on the oxygen.
What happens if I add a hydrogen to the oxygen? Now the oxygen becomes positive. Is that the electrophile now? Why is the positive carbon not the electrophile? I thought electrophiles were positive. The definition of an electrophile is an electron acceptor. How many electrons are currently around the oxygen? 8. So we've got 2 in each of those bonds, another 2 in our hydrogen bond, and we have a lone pair, which means 8 electrons. Can oxygen accept any more electrons? No. So it cannot act as an electrophile. Yes, our reactivity is centered around that oxygen because of the charge, but what does it do to stabilize that charge? It takes the electrons from the pi bond, making our carbon formally positive. I took a structure that was neutral overall, and I've now put a positive charge on it. What happened to the electrophilicity? It went up. So I could add a catalyst by adding a hydrogen, okay, adding a Bronsted-Lowry acid catalyst to go ahead and make that electrophile more electrophilic. Could I have done something else? And this is a distinct something else. We can make the nucleophile more negative. How can we convert one of those oxygens to becoming more negative? Let's take away a hydrogen by adding a base. The base pulls the positive hydrogen off, and now our oxygen has an extra pair of electrons, making it formally negative. Why did I say this is distinctly something else? Can I add both a strong acid and a strong base to the same reaction? No, they will cancel each other out. So we can only do one or the other, in the hopes that we can make it all the way to our acetal a little bit quicker. Okay? Questions on that? Guess what you get to do now? You're going to run under basic conditions. Talk to each other, figure out a mechanism. We want to try and get to the acetal, and I've given you that first step to work through on your own. Nucleophile attacks. We generate our negatively charged species. We still have that alcohol floating around as our solvent. That could protonate our negatively charged carbonyl oxygen. Okay, now what happens? We now have a hemiacetal. Okay, what can happen now? Carlos, what are you suggesting?
make the hydroxide with another hydrogen to make it water?
I like that idea. That's an interesting idea. Let's go ahead and add an H+. What's the result?
It attacks the base.
Now we got a good leaving group, right?
But where'd you get that H plus from?
Yeah, where'd you get the H+ from, Carlos? I'm confused.
If you did that in
Another
basic,
alcohol?
From another alcohol.
okay.
Right? So if you're getting it from another alcohol, we're saying that our alcohol initially here, our starting hemiacetal, is basic enough to pull a hydrogen off of another species, off of another alcohol.
Can it?
Well, that's the argument. Is one alcohol more basic than another alcohol? Or we could look at secondary structures, but we're ultimately comparing carbons all the way through. There really isn't much of a difference. Take it a step further. If I just drew out what we have right here as an answer, what reactivity would you tell me that molecule has? Got a couple answers.
It's an acid.
It's an acid. And in particular, that tends to mimic H3O+, which is a pretty darn strong acid. And we did under what conditions?
Basic. So it's-
Basic.
it's not gonna-
So I like your idea in theory, but in this circumstance, it's not going to work out for us. We can't protonate that. Okay. I still have a strong nucleophile. And yeah, OH minus may be a bad thing. So we'll cross that off as a bad mechanism. Okay. But what's it leaving into a solution of? Strong base. So yeah, it's a bad nucleophile, but it's a bad nucleophile in a bad nucleophile conditions. So relatively, not too bad. Okay? So we could go through and say that's our mechanistic step to form the acetal.
It's more reactive.
We've already suggested though, and what do you mean more reactive?
The OR with a negative.
The OR minus, that's what we started with, was being our stronger nucleophile. So we were hoping that that was going to work.
It's react twice.
Okay? So that works. That gets us to the acetal. What happens when we get into the lab? We run this experiment and we do not get the acetal. It stops at the hemiacetal. Okay, so you guys already started to allude to a potential option that the OH minus was a bad leaving group. There's something more important. It's an alcohol. It is an alcohol. When in doubt, what's the mechanism for that step? It's an SN2 mechanism. And in an SN2 mechanism, what do we want for our nucleophile? We have that, so why is that a problem? What's that? Yes-ish. Why? No, it's not going to be our issue. What substrate do we want for an SN2 mechanism? Secondary or primary? We have what is effectively a tertiary leaving group. What's going to happen under those tertiary conditions? That SN2 reaction is now not favored. We don't see that reaction occur. And that's all coming back to the mechanism, understanding how and why you did the reaction. So under basic conditions, we have the option, we have the ability to get to a hemiacetal, but we are stuck at the hemiacetal. It is very, very unlikely for us to actually push all the way to the acetal. So we came up with two methods to speed up the reaction, and one of them failed. Oh well. So what do? We go back to the drawing board and try the other one and see what happens. So guess what you're going to do? You're going to try the other one. I should have left in some arrows so we could take a look at this, but remember, under this reaction, we're now adding H+. Okay, this is our electrophile tweak. We're running under acidic conditions, so we supply H+, and we now want to see what happens in the course of this reaction. Okay, and again, I'll walk. Try that again. They cannot be p orbitals, because p orbitals do not involve direct overlap. What we're looking at is sp2 hybrid orbitals. That's how we get that shape. So you go all the way back to the very beginning of first semester. We talked about hybridization and said it's really important that you look at it and you know it and you understand it. Why? It's going to help us explain why this reaction works the way it does. Those electrons are held in sp2 hybrid orbitals. Where are the electrons from our pi bond? They're held in just p orbitals. What is the difference between a p orbital and an sp? Or an sp2 hybrid orbital? Why is the p orbital higher energy? Why is it further from the nucleus? There's no s character. The p orbitals are held further away from the nucleus. If you go all the way back to our molecular orbital and our atomic orbital theory, our p orbitals are further from the nucleus than our s orbitals. Which means if we now look at the reactivity of our sigma bond or our lone pairs versus our pi bond, we could make the statement that our pi bond is more reactive than our lone pairs. Which means, if we erase all of those strokes, what we would expect, oh, I didn't add arrows. Let me add an arrow. We would take the pi electrons out and react. Would we end up with the structure shown? No. No. What structure would we end up with?
Hydrogen would be attached to the carbon.
Nope. We would have two lone pairs on our oxygen and a bond to the hydrogen and positive charge on the carbon. What's the relationship between these two structures as they're shown? Resonance. Does it matter which pair of electrons you use to react with the hydrogen? Absolutely none. It can either be the lone pair or the pi bond. Why go through and look at the pi bond argument? Because that helps us eliminate our alcohol as a choice. Okay. There's another reason which looks at all sorts of more equilibrium things, and we'll deal with equilibrium later. Okay. Or that more complex equilibrium issue. The net result is, what did we do to the electrophile? It is now more electrophilic. So what can we do? We can take a now weak nucleophile in our alcohol and have it attack the carbonyl. Okay. Oh, this one I didn't add any arrows on. That was nice. So once it attacks, we now have our protonated alcohol species. Does our oxygen want to be positively charged? So what does it do? Take some electrons. Where could it take electrons from? Can either take them from the hydrogen, in which case we progress forwards, or takes them from our carbon and we progress backwards. Okay. Remember, our whole word association game last week was equilibrium. These are all massively equilibrium reactions. You have to be aware that every single step is reversible, and not only is it reversible, it is highly reversible. Okay? Once we deprotonate, what do we end up with? Our hemiacetal. That hemiacetal can do the reverse reaction as well. What does the hemiacetal now potentially do? What conditions are we under? We're acidic, so what else is present? Let's see, come on. So we'll skip to a new slide, just because it didn't fit. We still have H plus floating around. Our hemiacetal can react with that H plus to do what? Protonate the alcohol. What's special about our alcohol now? It's a wicked good leaving group, which means we can have it leave, and as it leaves a carbocation. Is the carbocation stable?
No.
If it's not stable, then we can't form it, and this step was futile.
Resonance stable?
It is stable because, what was your answer, Carlos?
Resonance stable?
we have resonance stabilization of the carbonyl, or of our carbocation. With that resonance stabilization, what happens? Carbocation does exist. This step was a valid maneuver. So now what can happen? We get this carbocation floating around in solution with another weak nucleophile, floats in, does our attack, and we end up with our protonated acetal. We can remove that hydrogen, and we now have our final acetal. Oh my God. Okay? We just went through, I think we had 4, 6, 7 steps. It's a bit rough. Of those 7, I think it was 4 of them were putting on a hydrogen or taking off a hydrogen. Why was it important to put on or take off that hydrogen? Why did we put it on to begin with? Make the electrophile more electrophilic. All right, so if we go backwards, let's see if it actually does. Oh man, I'm going to stepwise it all the way back. Our first step, we put on a hydrogen. All right, so this was an acid-base reaction. Added a hydrogen. All right, then what did we do? All right, we had our nucleophilic attack. So we pretty much did a sort of substitution. It's a little bit weird. We substituted an oxygen bond for a pi bond, so it's really an addition. Okay. So our acid-base step was really our addition, step 1. The next step was our addition, step 2. Then what did we do? We deprotonated. Why did we deprotonate? To stabilize our intermediate so that it could actually form. Right? Then what happened? My God, we protonated it again. Right? Why did we protonate it again? Made it a better leaving group. So we did another acid-base reaction, which is really the, that's what I was about to just erase. Our SN1, step 1. Followed by, okay, this is actually our step 1 officially of our SN1, followed by our last step, which is our SN1, step 2. And then again, another acid-base step. So nearly every step within this reaction was an acid-base step, done for very particular reasons, either to stabilize our structure or to make it more reactive so that it could progress forwards. How did we know that we wanted it to progress forwards? We went into the lab, we did the experiment, we got this result. We now have to come up with a way to explain that result without creating any structures that would invalidate the conditions under which we worked. Okay. Is that insanely tricky? Yeah. That's why acetals are kind of a bit obnoxious. But that's the way it works. Okay. So we can go ahead and take a look at our summary for our alcohols. We've got the full mechanism up there. You'll notice that I only gave you the acidic mechanism. Why only the acidic mechanism? It's the only one that actually takes us all the way to the acetal. So that's the one you're going to be primarily responsible for. A lot of individual steps, almost all of them are protonations or deprotonations. Does it matter when you do it? Absolutely. Because that's going to change how the reaction works. Okay? So for all of you now saying, oh my God, I got another mechanism to memorize. Stop memorizing it. Focus on what happens with the chemistry. You are finding a positive, finding a negative, and putting them together. Okay? Our official summary is on the far right, going from our carbonyl, first to the hemiacetal, then all the way to the acetal. If I want to form the acetal, what I'm going to do is limit the presence of, look in just that far right column. If I want this species, the acetal, what do I need to do? Get rid of the water. Remember, it's an equilibrium reaction. If water's present, that's going to push the equilibrium back the other direction. So if I'm going to form the acetal, what I'm going to do is keep water out of that reaction as long as I possibly can. And if it means distilling it or adding drying agent or doing anything else like that, I will. Okay, what else could I do? Whoops. Really not responsive today. I could add in an excess of one of the reagents. The one that I'll add is probably the alcohol. Any ideas why? What's the mole ratio? It's 2 to 1. So it makes a lot more sense to add a lot of the alcohol because it's already in a 2 to 1 ratio. If I add more of the carbonyl, I would expect to end at the hemiacetal, not at the full acetal. Another primary reason why we add the alcohol is it's also cheaper. Okay? So we'll add a lot more of the alcohol because we can get away with adding a cheap reagent. Okay? So, more practice. What I want you guys to go through and do is identify the following structures. We just got 3 of them. That's 3. 1, 2, 3, 4, 5 structures. And identify them as either a hydrate, a hemiacetal, an acetal, or none of the above. One extra wrinkle in it, if you happen to get done with that in faster than 3 minutes, determine what alcohols and carbonyls were used to make the hemiacetals or acetals. Okay, so you got a bunch of different. Well, there's no additional alcohol added to this. To get it to form the acetal, do we need to add anything? Yeah, what do we typically add? Acid. Why do we add the acid? To speed up the formation of our product, or speed up our equilibrium for it. So we do add acid in this case. Is it necessary to make it? No. And in this question, all we are asking for is what was the starting alcohol and carbonyl. In this case, the starting alcohol was the starting carbonyl. Okay? Second to last one, our answer is acetone and what, methanol?
Basic.
And methanol. If we want to push particular conditions, if we run under acidic conditions, we would expect to see the full acetal. Since we're stalled at the hemiacetal, we could also go through and say we're probably running under basic conditions. A little OH minus. Actually, OH minus is a bad option. I'll mention that in a second. Probably run under just basic conditions. Why is OH minus a bad option? It's a competing nucleophile. And number 2, when OH minus reacts with our alcohol, what do we make? Water, which takes us the wrong direction in our equilibrium. Okay? Last one is none of the above, so I'm not going to bother to draw that one out. Questions? You want to try 2 more on your own? Give you 5, 4, 3. Is that a yes?
Yes.
Yeah.
Okay, thank you. Time's up. Cyclohexanone and a diol. Really important, that diol. We'll talk about that one in just a second. Next one. What's tricky about that next one?
It's a heptanol or heptadiol with a ketone.
In this case, our alcohol and our carbonyl are in the same structure, just like our last one was, or from that tricky one from the last page. What makes this one even trickier? I'm showing the oxygens attaching on opposite sides. Okay. So now that all of a sudden looks like it's not an acetal, it is still an acetal. What I would go through and do, actually, in this case, would be the one case where I would say it's okay to go through and draw it out. Because you all are doing the exam in pencil, I would then erase those bonds. There's my carbonyl, hydrogen, hydrogen. There's my answer. Okay. If I needed time, then I could go through and redraw it out. How many carbons?
7.
1, 2, 3, 4, 5, 6, 7. I can now draw in my straight line structure, and I could get to my final answer.
Does stereochemistry depends on the rotation, on the free rotation?
So, interesting question. Is this molecule chiral?
No.
Yes. Yes, it is. Okay. There are not 4 different groups, but if you look at the geometry of that structure, we do end up with a chiral center. Or at least we do have an issue with this potentially happening. Okay. It'll be non-superimposable on its mirror image. You'd have to draw the mirror image and be able to deal with the 3 dimensions to overlay it on top. Is that an easy thing to do? No, which is why you've never seen it asked. You might see it asked in an advanced chemistry test, not the ACS.
Would you still classify as an S or an R?
No. It does not fit under the S or R rules. You just say the molecule is chiral. Okay? Other questions on this? Okay. Acetals, 3 more quick questions. All right, this is a fun one. Which side of the reaction is favored? I'll give you 30 seconds. You can talk to the people quickly around you, come up with an idea. And continue then. So, some of you noticed that this question was a lot easier than it needed to be. Because
It already tells you.
look at the arrows within the reaction. Okay, our equilibrium says in that first case, the bigger arrow towards the right means product is favored. Okay, so we've got one easy answer for that, for pointing out our products are favored. So that was the easy answer. Make it more difficult. What's the hard answer? Why is that equilibrium arrow used? Nope. So acidic conditions does not push one way or other. So a catalyst does not change the equilibrium. It just gets us there faster.
Is it because you have more alcohol than you do the other?
No, we need alcohol to go through and do it, and we need those 2 alcohols. It's not going to be it. And water is not going to help either. If we were removing water or we added excess alcohol, yeah, that could help favor it, but we aren't saying anything about excess or removal.
Aldehyde is more reactive.
What was that, Carlos?
Aldehyde is more reactive.
Our aldehyde functional group is a stronger electrophile. Let's take a look at that. Our carbon there is being stabilized by hydrogens. Does hydrogen really have any electrons to stabilize that carbon? No. So what does the carbon do? Seeks out another electron source. What's that other electron source? The oxygens from our alcohols. So in this case, we would expect the product to be favored because the aldehyde is so darn electrophilic. Okay? What about the next one? Where would we expect the equilibrium to lie with this one? It should be with the ketone. Why does it stay towards the ketone? Electron donating groups which stabilize that carbonyl carbon. There's another reason. It's the answer that almost everybody skips over. It's not that big of a deal. You didn't skip over that one. Sorry. You guys got that one really, really fast. That was way faster than I expected. It's a hint. More molecules on our reactant side, entropy favors our reactants. Last one. So these are borrowed from a different textbook, so that's why you got all these extra colors and stuff, and also why the equation doesn't quite fit the same pattern as the other 2. What we're ultimately looking at is our equilibrium to go from our starting to our acetal. Which way does the equilibrium favor? This one's pretty hard. Is there an entropy factor? It's 2 to 2. We're looking at a ketone, so that might favor our reactant. Okay, so we might lean more towards the reactant. It turns out that in circumstances like this, and this is an important one, we tend to favor the product formation. Okay? The reason being, our first alcohol attacks and we generate our hemiacetal. That species can fall apart or can continue to go through to the acetal. In the case of our other circumstances, we had to have a second molecule come in and interact. So that means a second molecule has to diffuse through the solvent to get there. Is a second molecule involved at this last step? No, it's all happening within the structure. We don't have to wait for a second molecule. That second oxygen is already there and ready to react. Would this work as well if we generated a 4-membered cyclic ring?
No.
Why not? Sterics kind of work. Our bond angles have to crunch down too much. So what we're looking at in this case for our cyclic 5- and 6-membered rings is we end up forming a really stable ring structure. That really stable ring structure is what allows for that formation. Why is this of critical importance? We can use it to now protect our carbonyl. So if I wanted to do some chemistry somewhere else on my cyclohexanone that could get affected by that carbonyl, I can now throw in this diol starting material to turn it into the acetal. I now no longer have the carbonyl. It can't react as a carbonyl. But when I want the carbonyl back, what do? Just add a bunch of water and acid to push it back the other direction. Ethane diol, yeah. So if we go back to the initial question, what I'd asked was that first step. Okay? To go from, and it may look a little bit different because I actually rearranged it. Yeah, I think I drew it as a straight line. To go from our carbonyl to our diol. To go through and do that, we have to go through and protect the aldehyde. Then we could reduce the ester. Then we can deprotect the aldehyde. So to do that one step, simple structure A to structure B, we have to do 3 things. Protect, reaction, protect, or deprotect. And that's what's happening in between. We add our diol, our ethane diol, because what that's going to do is give us that cyclic 5-membered acetal structure, which is stable enough to form. Once that forms, we're now fantastic and ready to move forwards. Okay? Yes?
The diol will only work with the aldehyde or ketone. It won't involve the ester?
It will not involve the ester. Why would it not involve the ester?
Resonance.
The oxygen from our ester resonance stabilizes our carbonyl carbon, neutralizing its electrophilic characteristics. Since it's now no longer electrophilic, our mild nucleophile isn't going to do anything to it. Okay? And I did copy this one from the textbook too, and they missed a step. This would be our LAH, and then we'd have to follow it up with our H2O and H+. Okay? Questions on that? Kind of crazy. So we add the protecting group, do our reduction, remove the protecting group, then what do we do to do that last step? Kind of, sort of. H+. It reacts by itself. All that structure is the starting material of the one to the right. Those are the acetal and carbonyl partners. Okay? Yeah?
The top structure, when you add the acid, then the water, and then when you want to go back in the other direction, you do water, then the acid? Or
The acid is just a catalyst, so what they're showing with those brackets is not separate steps.
It's not a separate
It's not separate steps. If we want it as separate steps, you will see 1 and 2. So what they're showing in the very top reaction is that we have to add our diol. Whoops, don't number that. We have to add our diol, and we add an acid catalyst. the net result is that we lose water. All right, so they're trying to cram all that information into one space. Okay, next new thing that's going to happen, because we've already got some people complaining about the speed. I understand that. So what we're going to do is switch it up. The lecture on Wednesday is not going to be a lecture. What it will be is just problems. What I will do is go through and record a lecture and post that. And I will do that sometime after lab today. It will get posted tonight. You will have access to it, and what it will go through and do is look at the rest of the slides. So we've got one more case for oxygen nucleophiles, which you will probably never ever see. And then it goes through into our nitrogen nucleophiles. So I did switch up the order again just to kind of match things appropriately. We'll do a whole bunch of nitrogen nucleophiles. I'm going to stop recording because that's going to